I'm going to go ahead and just introduce this remote meeting. By the way, I'm streaming this onto Twitch. I think there's 6 people watching on Twitch. And I will probably take a recording of this and maybe put it on YouTube because that's where I have all the other Hackers Hangouts. So welcome to the HTM Hackers Hangout. This is probably like the 100th one of these that we did. Although I haven't held one in a while, mostly because I've been live streaming so often that like the Hackers Hangout was sort of a way for you guys to see what we were thinking about and give feedback from the community. But I've gotten so much feedback from the community just opening up live streams and chatting with people in the chat room that I haven't made it a priority. So this is the first HTM Hackers Hangout that we've had in quite a while, quite a few months. So I just saw Max Lee join. Thanks for joining. For those of you who have something that you want to present, I know I have on the schedule Max Lee, Jordan Kay, and Marty Chang. I don't think I've seen Jordan yet, but he might want to talk about actor models. And then I'll open it up for anybody to have that has a topic. But for right now, let me just say that there's a lot, and at least 2 of the speakers from the community tonight are going to be talking about distribution models, or ways of taking the computation that we talk about in HTM and distributing it across multiple nodes, and how those can be cut up, like at what granularity we can cut those up, cut those processing up by region, by cortical column, or by layer, perhaps. These are all open questions. Like, the best way to do this is unknown. So one of the biggest areas to do this in, or platforms, is Elixir. So I think both Max and like there's another guy on the forum, D-Led or Dimitri. He programs HTMs in Elixir as well, and those, I think, are come with this actor model. And it's I'll let the other people talk about it, but my questions, or my big questions, are just because Namenta is not working on this at all. As far as I know, we're not working on doing distributed HTM processing in any way. So it's super cool for me to see the community working on this, because it's obviously something that everybody understands is valuable work to do. I'm going to just throw some open questions out there, and it's mainly like, where do we break it up at? In one of my HTM school videos called Cortical Circuitry, I think, I proposed that a layer would be a good modular unit to start at, because it's got input and output, it represents something, and it is a process that's doing something that could be different from another layer. So I sort of already threw that out there. I think that would be a good place for the distribution to occur. But breaking up a layer, it would be really, really hard, in my opinion. Like, ideally, though, like if you had all of the compute process and parallelism that you could do it like the brain, which is essentially like every neuron is its own node. But I think we're pretty far away from being able to do that at this point. So I think like targeting either a cortical column or a layer within a cortical column is a good target for anybody to shoot for at this point. So that's sort of what the community topic is. It just sort of emerged. And I'm going to let, I think, Max, if you're ready to talk about HTM and Elixir, you are. So you can share your screen if you want to, and I think you can unmute yourself too. All right, I got your screen.
Hey guys, can you hear me, first of all?
Yep.
All right, cool. Yeah, this is my first time participating, so I'm usually always busy, but thank God for this damn plague, have a little bit more time in my hands. So, something positive. Yeah.
Thanks for joining. Yep.
Yeah, I mean, so basically for me, to start back in like the end of 2018, I thought, hey, this seems like something that should be easy to implement and distribute. And I was wrong, by the way. Ran into walls, crashed and burned, and it languished until about a month ago. And in the meantime, I'd always been working on it, chomping on back in the back of my brain, and thinking, okay, well, here's how it would work. So I guess me start this. This is just really quickly thrown together. So I have a GitHub repo right now called Elixir HTM, and the reason why I decided to go with Elixir is because of very specifically the Beam virtual machine, which Elixir is built on top of. So I guess you have the Beam virtual machine, you have Erlang, and then on top of Erlang you have Elixir, just sort of acting as an intermediary translator, compiler sort of thing. The advantage of Beam is that it was developed by Ericsson to run their managed phone switches way back in late 80s. So they designed it specifically so that it was distributed, so that you could perform service without taking out an entire set of phone calls.
Now, is Ericsson behind Erlang and Elixir too?
They're still behind Erlang, but not Elixir. Although I guess the two communities have a lot of back and forth and have influenced each other. But yeah, Ericsson is still providing Erlang and updating it actively to kind of meet modern CPU architectures. Yeah, so what I really like about Beam is that it just automatically will distribute tasks across however many cores you have. So, I have a Threadripper in my system at the first generation Threadripper, so I can use up to 32 schedulers. So, I can spawn 100,000 tasks, 200,000 tasks, and it'll just distribute the load automatically across that and process it and very actively preempt each of those operations so that everything gets done in short order. The advantage of this and sort of the emergent architecture that happens when you start developing something in Elixir is that you start developing processes. So very naturally, you will have, you'll have your server process, and then when your server receives a connection, you don't want to have your entire thread occupied. Instead, you create that socket, and then you hand it off, and you spawn another process. Meanwhile, that continues doing its own thing, and your server continues accepting incoming connections. So that's sort of what has emerged naturally over time with Erlang. So they built an entire library around it called OTP, or the Open Telecom Platform, which is kind of a misnomer. But the concept of it was how to generate these processes within the virtual machine and not have the whole thing keel over. The other benefit of it is that if something did go wrong, so you have all these distributed processes, if something blows up, only that process dies. That every other process is otherwise isolated, and that the Beam virtual machine as a whole continues on. So this is nice. If any of you have ever done IT support, with application infrastructure, having to update or even make changes to a live operating system, this is a good way to do it. It lets you live compile code and then push it so that currently active sessions of running the previous version of the code, whenever they finish, they'll just automatically respawn up with the brand new rendition of code. So it's kind of neat. Anyway, so that's all the IT background behind it. Now, what I've actually been thinking is how to divide this up, kind of coming back at the whole distribution question that Matt's been talking about. That in my mind, that the way that I visualize it is that you have the pool, but really, what is the pool? The pool is nothing more than sort of like a container for all of the columns that happen to be in your system. Whatever encoding bit length, whatever encoding you have coming on, basically your pool is managing that and sending it off to the columns. So that's the way that I have coded this. So when my code starts up, it starts the pool. The pool says, okay, I'm going to accept or expect a certain encoding length, like 100 bits or 1,000 bits, whatever. Then On its startup, it spins up however many predetermined number of columns. Then the way that I have it written at the moment is you send in just whatever bit encoding to it. The pool then distributes all of that across all the columns, just broadcasts it out wide. It says all the columns, here you go, take it, do with it what you will. Then each of the columns will go through, they'll do an overlap score. So based on what their distal connections are to the input space and what the encoded input is, it'll just do a quick comparison score saying how much overlap is there. It will then report that back to the pool manager. And then the pool manager will say, okay, well, all 10,000 columns have reported back in. Based off of the average score distribution, I'm going to choose the top 60 that are above whatever threshold. And then keep in mind, all of this is happening in parallel at the same time. So the column processes are just chilling out there waiting for some sort of message. So the pool manager then sends a message back out to the winning columns only saying, hey, you've won. At which point the columns then look at, okay, what was the encoding that we received? Based on the overlap, it would strengthen the overlap connections. And I haven't coded this yet, but it could then, theoretically in the same pass, weaken the non-overlapping connections. Just so that way each column would start to recognize a pattern.
Max, I just want to clarify something because this, for a long time for me, was endlessly confusing. The columns you're talking about are mini columns. They're not Correct. Cortical columns.
Yes.
Just to be super clear, because I was referring to this in a way where you would do it with mini columns as a node, but these are mini columns, and you're talking about the K-winners. We're talking about spatial pooling right now.
Yes. So we're talking only the spatial pooling at this moment. So I guess that kind of brings us to, if we go look at the pool manager process here, that that at the moment we're talking about step 4, and then what happens is that once the pool manager sends out, okay, you're the winner message to the columns that it chooses. They then go through, if it wins, it'll strengthen the connections. And then only at that moment does it then begin choosing the winning cell within the mini column itself. And the way that I have coded this is that this winning cell inside of the mini column isn't actually any sort of entity. It's just a key and a map. So you'll cycle over through for all the keys in the map, which one has the most connections or the least connections or whatever criteria, and then say, okay, you're the winner. At that point, it reports back to the pool manager saying, okay, for my cell, and here's my column ID, here's the cell that we randomly chose to win. And then the pool manager will keep track of that.
So each mini column keeps track of its proximal connections, right? Its potential pool to whatever Correct. Input it is.
Yeah. Its proximal connections essentially as a key to a map, and this is just a map of lists of connections. The way that it is keeping track of the temporal aspect of it is that when this column wins, so it says, okay, choose winning cell. At that moment, it takes the previous time steps, winning column cell combinations, and actually sends a message to those winning columns saying, hey, here's my column ID, here's our winning cell. Next time that your column with this winning cell wins, call us. Just send a message to us. And then what happens inside of each one of these columns is that during this sort of, at the end of every time step, when all of the winning columns and the winning cells have been selected, they're messaging out to the next time steps columns saying, hey, I think you might be called on. And then that will put it into a potentially predictive state. So basically, all of the winning columns from time step -1 call on the current time steps predicted winning columns to say, hey, you might be firing right now. And so basically by doing this, we have, you have the pool, and the pool basically keeps track of who are the winners at a given time step, who are the winners at the previous time step, and sort of coordinating, choosing the winners and telling them to strengthen or weaken consequently. And this works. Like this works really surprisingly well. So let's kind of go to crappy demo time. Where's our other? Not quite that. Sorry, I have way too many browsers, guys. My apologies.
It's all right. I remember the first time I wrote a spatial pooler and tested it and realized that it worked. I was sort of floored too. It just seems a little too simple, right?
Yeah, no, and it was surprising. So okay, the setup that we have here is, so IEX is the sort of command line interpreter that you pull up for Elixir. And it really just acts as a thin interface on top of the Erlang interpreter. And so you call it with IEX-X and S mix to bring up your code. And the Beam virtual machine itself has this nice view utility that you can call using observer.start. And it brings up this nice GUI that gives you different details about what's happening on inside of the machine, different load charts, all the different schedulers to show the 32 potential threads that I have for my CPU, memory usage, all that. So this is a really crappy way to do it, admittedly, but it was quick and dirty. So I have these URI endpoints that basically, let's say we want to start a new pool, and we expect that the input encodings will be 100 bits long, just cause. So you see quickly over here that it went through, it generated the random initialized based on number of parameters, so like connection space, number of connections, and whatnot. It created a basic list of that then every column upon initialization will receive a copy of this, and then randomize it for themselves. And so that's how I deal with initial input encoding space, distribution. So, that's neat. So this means that, we have our pool that started. We have our columns that are floating out there. And even here, we can see our memory usage jumped up from what had previously been about 50 megabytes to, let's say, maybe 400 megabytes total. And at this point, you start seeing a little bit of activity on the virtual machine across the different schedulers. The overall number of processes that we have, and our hard limit appears to be, what's it? 262,000 at the moment. And you can adjust this if you dig down into the virtual machine. I think you can give it anywhere. However much RAM you have, it will support basically.
So have you just created the space to compute, or is it computing anything?
At this moment, you just have 10,000 processes to represent 10,000 mini columns, just chilling, just doing nothing right now, just waiting for some sort of message. So, for example, like if I go try to check the state at this moment, I think if this doesn't crash, it should just be a blank list, or it's not. Apparently, it's nothing. So never mind. It's not updating. So let's just send in, as a quick example, we have the SDR endpoint, which is sort of a misnomer. You should probably call this encoding or whatever, pool input. But here's our long bit sequence. It's just ones and zeros. And if I send this in, let's see. Is this not working? Doesn't seem like it's... Okay, so let's redo this. Aha, there it is. All right. So, let's do this again. Send in a new one. All right, cool. So right now I'm sending in each of these encodings, and you see sort of as it's going through handling, the server request and parsing stuff through. But what I've been paying attention to is the number of seconds that it takes to for all of those 10,000 processes to report back in. So they've gone all the way through the process of doing the overlap score, reporting back to the pool choosing the winners, telling them to go strengthen connections, and then those winning columns to report back to the pool manager saying, okay, here's our winning cell. And this whole process for 10,000 columns is taking us, if we do one more time, at the moment, because there's a bit of activity happening on my computer, it's taking anywhere between 350 milliseconds to 600 milliseconds. When nothing else is going on, it is anywhere between 200 to 300 milliseconds for 10,000 columns, and it scales linearly by the power. So 100,000 columns, it takes about 3 seconds to go.
That's
one
pretty,
thing that kind
pretty
of
good.
Yeah, it's pretty decent, and this is just running on a single machine. The one thing I have not tried yet is bringing up another node on my laptop across the room and distributing it that way. But this is decent. This is definitely not the most efficient way to do it. For example, I'm using long lists of essentially tuples, and basically I'm not doing it in the most data efficient way. It's a pretty naive approach at the moment, and sort of a lot of the ways that I'm approaching the algorithm were just sort of quick and dirty, shoot from the hip implementations. So there's definitely room to improve even as well. The other thing that makes me excited about it is that even though the temporal aspect of it is nice, it's really nice. If I turn that off and say I bump it up to 100,000 or 200,000 mini columns, just so that it can learn the spatial aspect of it, that it's taken about the same amount of time to do that, so that could scale very easily. So what is it? That company out there that's already using SDRs as fingerprints to represent natural language processing.
Cortical IO.
Yeah, cortical. Yeah.
That's interesting. So you can.
Yeah,
so it's faster to scale up. Sorry.
Yeah, they're not doing any temporal stuff at all, as far as I can tell. This, I feel like, would be a really quick and dirty way if we were to make a homemade version of that, for example. Okay. And then finally, and this is kind of a work in progress, in order to get the pool state out of it, is just to literally, this sends back the list of of states and sort of concatenating it toward the end here. All the columns as they report in saying, are you active or not, basically. So you can see a majority of them are not active, as far as we can tell, before it gets chopped off. So it's ugly, but it works. The main thing I'm gonna try to put some work into is making it a little bit more visual, and perhaps make it so instead of just doing raw URI parameters, use JSON as input and be able to parse that. The other potential for this, by the way, is that instead of just having a single pool, there's nothing to stop us from saying, I have this one encoder, this type of data. So pool number 1 is going to be receiving FFT data, for example. Pool number 2 is going to be, locational, whatever sort of concatenated data you choose. So you can start dividing up and creating different pools to represent different regions. And again, there'd be nothing actually stopping you from saying, all right, across all the pools for this time step, all of the winners create connections with each other.
Yeah, that's interesting.
Yeah. The other aspect of it, and sort of what I'm intending it to do, is by having it be in sort of an API format where you're just making API calls, that you can start getting more, resource constrained devices, like ESP32 or it's a simple little FPGA implementation. you can have all these, instead of having to do all the processing on device, they can just be sending these API calls and receiving, responses back to manage different local state machines. So I feel like this feels like to me a really decent way to scale things. But I'm more than happy to be wrong if somebody can do better. And I'm always happy for anybody who would want to start hacking on this as well and expanding it out. I'm at all not married to any particular aspect of it other than the fact that it seems, at least having the pools and then the columns and not breaking down any further than that, that seems to be the most logical way to go about doing it. The other aspect of, so the code has changed only slightly over time, but on the forum with this implementation and actor model, I should probably create my own separate thread to sort of keep track of Elixir HTM instead of have it be spread about. But this kind of is giving a code view of what is happening, what's calling what, and how. It's, lacking a little bit of its detail in that, it doesn't include any of the temporal aspect at the moment, for example. It's slightly out of date. But maybe I'll just copy all this and update the README in the repo, and then keep it updated there.
Yeah, and
I know there's not a lot of experienced people who are using Elixir out there, but I feel it's compelling enough that as long as I can make it approachable, that anybody should begin to hack on this if they feel like it. So.
Well, I'm hoping that Dimitri's watching, because I know he's really interested in Erlang and Elixir, and even Fergal Byrne. He's talked about an HTM implementation in Elixir for years. So hopefully they see this video and see your implementation.
It's not perfect, but it works. So,
so I wonder if we could talk about this idea you had about the winning columns connecting to each other sort of across regions. So I think that's interesting. I mean, if Jeff were here, he'd say that's not the way the brain does it, probably. But
and,
at least I
was keep Jeff's little. No, that's not how it really works. Thing in the back of my mind as I'm coding, I'm like, no.
Yeah.
Like, can I make this compromise? So.
Well, we're in the engineering world here. So I think that you're free to take whatever shortcuts you think work. And I think we're going to find the more we understand about this, the more we realize we can do with it that it wasn't meant to do, just like any new technology, So yeah. I would say push those boundaries a little bit and see what happens when you run into a situation where, wow, this is interesting. That's an indicator to move forward with that thought a little bit.
Yeah, I'm open with this. I mean, I want to potentially, like, if once it gets a little bit more rounded off, I do sort of want to make this into a service just floating out there. So you can register your API key, start up your pool, and then send stuff in and out and do with it what you will. So if it gets to that point, then we'll probably have to have other conversations, but yeah.
Thanks a lot, Max.
Yeah. That
was very cool of you to. Well, I sort of asked you to volunteer to show your work.
You know what? I kind of believe in this. I think this is the way that stuff should go, as far as scanning out. I think maybe Martin might have other ideas about the speed and performance of it, but I'm okay with that. The thing with Elixir is that it is extendable. We can call native code out from outside of the virtual machine. Say we have a local implementation that's faster on a specific hardware. There's nothing to stop us from using this distribution model and calling that native code. So, yeah, cool.
All right. Speaking of Martin, we could probably, unless why don't we give people a chance to comment or question Max before we move on?
Yeah, I have a question.
Yeah.
if you're not rocking a Threadripper CPU, is the idea that you could easily distribute this across multiple machines?
Yeah, well, that's the Beam virtual machine. That's one of the things that I love about it, is that it kind of has built-in ideas for distribution already. All I need to do is, open an Elixir, command line client on my machine over there. Make sure that they have the same secret key, and then there they are. They can talk to each other and distribute that way.
Yep. So then you just have whatever network bottleneck existed between the two or more.
Correct. Yeah, which gets the same. You're running into the same limitations at that point as everybody with any distributed network application. So.
Hey, Mark, I had to mute you because I was getting some feedback, but go ahead.
Before the meeting started, we were asking if anybody's had any success with doing multiple areas or maps of the brain talking to each other. How do you feel that would fit in with your scheme?
There is technically nothing at all that would prevent that from happening with this. So I'd have to make a minor code modification of about 3 lines to be able to generate multiple pools. But then as far as, the winning columns amongst those pools communicating with each other and saying, hey, set us into a predictive state. There's nothing at all limiting that, nothing. So, yeah.
All right, last chance to talk to Max, and otherwise, hopefully Martin can share his screen. Good to see you. I don't hear you though, Martin. Thanks a lot, Max, and nice to meet you. I don't think we've ever actually virtually met.
Yeah, I'll try to participate a little bit more now. Things are slowing down, and I've been purposely trying to scale back. So.
Well, that's a great contribution to the community.
Yeah.
I think we're still working on getting Martin's audio up.
Is it working now?
Yes.
Yeah, great. Let me try. Okay. So where do I start? Let me have a look at my notes. Okay. So many of you might know what Attler what is. Sorry. Can you hear me now?
Yes.
Okay, great. This is better. So a lot of people should have known what Attler is by now.
Thanks, Big L, for subscribing.
HTM implementation I built for my graduation project. Now, the core design I built Attler. The reason I built Attler is because I tried to run a reinforcement learning experiment using HTM.core, but it turns out every time step took me like 30 seconds to simulate, which is a bit too long for my liking, so I rebuilt the entire library from scratch. Oh wait, I didn't share my screen. Hang on.
I was just about to say something.
Yeah, I forgot to share my screen because I have 2 devices. Where is video sharing?
There should be a big green share screen button somewhere, easy to find. On the Zoom interface.
There's a start video section, but where's the share screen option?
就是视频里面最下面的按钮，就是绿色的那个 share screen。
Ah, thanks. Anyone can you see it now?
Yep.
Okay, so let me restart. The reason I built Attler was because I want to run HTM experiments for my graduation project, but when I'm doing experiments, I find HTM.core running way too slow for my liking. That I have to every time step took about 30 seconds to simulate. So I rebuilt the entire library from scratch, which is mostly centrally designed around the concept of getting HTM run faster and faster on a
This is
single
really
machine.
impressive.
And so
The logo looks
what
great
I
too.
did was I just deconstruct the spatial polar and temporal memory operations into different blocks. So there's the input, and there's the cell activation, and there's the boosting and inhibition. And also for the temporal memory, there's input and other stuff. So these are like the tensor operations within frameworks like TensorFlow and PyTorch. So let's say you have an input SDR, and you run the column activation, then inhibition, or you use the activation as a prediction. This way we can write different operations, then optimize these operations individually to just build stuff faster. And talking about PyTorch and TensorFlows, I just decided that probably tensors are a good idea. So all my inputs are implemented as tensors. They are dense arrays instead of what we are used to in the HTM system are sparse. The upside of the dense arrays are that they are really efficient in terms of CPU cycles. You can just scan through the entire array and you have your ones and zeros, instead of you have to count the indexes and determine where are the ones. So you essentially get an O1 operation instead of a ON1. And there's really not much interested about framework in terms of the architecture. It's really just like PyTorch and TensorFlow, and in terms of distributing the different layers across the different layers, instead of what Max have done, instead of what Max done was you distribute every mini column into different processes. Attler distributes every layer, every spatial polar or temporal memory into a different processor. So maybe my L4 here runs on the CPU. I can send the output from L4 on the CPU to the L3 on the GPU or FPGA or something. Then every of these blocks can be implemented on a different processor. So let's say if we have a 8 GPU server, or even a server farm, where we can have thousands of GPUs, we could have a layer running on each GPU and send the data across from GPU to GPU or server to server. And the parallelization model on the GPU or CPU is really not fixed. As long as it can do the operation, there's really no requirement for how the tests are distributed, as long as they are finished in time and correct. So yeah, that's the core design of this architecture. And
so about the tensors.
What could I say? So I would like to show a bit of a Python demo, but I'm still working with the binding authors to fix the latest binding not working on most machines. So I would have to deal with C++. So I believe many of you have used either NewPig or HTM.core before, right?
I think it's safe to assume some knowledge of that, yeah.
Oh yeah, okay. So in HTM.core, if you actually you want to code a encoder, you say, I want a scalar encoder, and we just code encoder.encode to encode to get the encoding out of your scalar. In Eclair, we simply say we have a SDR, and only in Eclair only encoders are scalar pure functions. They are functional. So it's stateless, and it's a lot more PyTorch and TensorFlow-like. So we can simply say SDR equals encoder grid cell to be, and we just give it a random position, like, I don't know, 100. And it will give us an encoding of the location. And the same for a spatial polar and temporal memory. We can simply say SP equals a spatial polar, which takes in the SDR size and generates 64 bits of output.
You missed an R in spatial polar.
SPATI. Oh, yeah. And we can simply say sp.compute to get the output. Oops. Out. Yeah.
So you missed a T in compute.
Oh, and also
gosh.
Spatial polar is spelled poorly.
Yeah,
I think you're just because you're coding in public. This always happens.
Yeah.
This is my worst nightmare.
Ah, great.
And my server wasn't responding, so it's all right.
Yeah, it always happens. Do I really have to do this? Should work now. And where's my spatial polar? POL polar. So SP does exist now, and we can just compute of SDR, and we can just pass the SDR into the spatial polar, and we'll get the representation that the spatial polar thing it has. And
nice.
We could also use the GPUs, like GPU equals make. I don't know if I have GPU implemented. Hang on. Enabled for backend. OpenCL back.hpp. GPU equals make sure.
This is pretty impressive, Martin, because this is like one of the most technical code demos I think I've ever seen.
Yeah, I'm not used to live coding, so anyway. Yeah, great. So a quick demo, so we could just run sp.to GPU and sp2 anyway. Sorry, and the GPU. Great. Okay, so now sp2 runs on the GPU.
That's cool.
Imagine your server has 8 uploads and you have 2 CPUs. You could have 2 CPU backends and 8 GPU backends to share your load across whatever you are doing.
That's pretty cool.
Yeah, and my original idea was to have one of these cards which have 8 CPUs on them, and they have enough bandwidth to run HTM individually and just share data across them. So each server could have potentially up to 64 layers running simultaneously. But these are too expensive. Oh yeah, I said I want to share stuff about the IC development side of stuff. So one thing we have been doing recently in lab and research was to try to build a HTM-based accelerator, like what people have been doing for neural networks, which we have been running into multiple problems. And the most important one is there really isn't enough memory bandwidth for running HTM on normal systems. Anyway, one of the most biggest bottleneck we have run into in developing Etaler was we find that we run out of memory bandwidth really, really, really fast and very early. So unlike neural networks where we have an input image and we have an output to something and their weights are reusable, in HTM, your synapses and permanence are not reusable. So we have to stream all those data from the memory constantly, which uses up a lot of memory bandwidth. And so we are trying to find ways around this problem, but there really isn't much of options. So because you have to have those data. You can try to predict what's useful, what's not, but that's only going to give you a fraction of bandwidth compared to what you need. So yeah, the biggest problem is we don't have enough bandwidth, and a potential solution is to just build multiple memory controllers onto your chip. But that's very expensive, and because memory controllers are expensive on their own, you have to buy the IP cores and they are very large on the chip. So the chip space, they use up a lot of your chip space. And because normally we prototype our chips on FPGAs, which you can think them of like chip emulators, where they have logic gates built on them, and you can connect those logic gates to build whatever you want, like these stuff. But the problem with FPGAs is that they normally only come with one memory controller layer, so we can try the multiple memory controller approach. So, without multiple memory controllers, there really isn't a good way to accelerate HTM on basically anything. And we have seen people talking about the spiking neural network accelerators on the forum somewhere. I need to pull it up later on. But the problem with building those architectures on the research side is, again, we don't have enough memory bandwidth. So using the neuromorphic architecture really doesn't help in our case of building HTM chips. Yeah, so that's what's happening on the research side of the stuff, and yeah, that's about what I'm doing now.
Thanks. Are there any questions or comments on Martin's presentation on ETLR?
I guess one basic thing that may have come up on the forum before, because it's often one of the first things that comes up when the GPU comes up in the context of HTM. You show the spatial pooler here. Yes, that can certainly benefit from the GPU. The temporal memory, usually it has many cells. Like it requires an enormous matrix. If you have, like, for example, 65,000 cells, mapping to 65,000 cells, that becomes a very big weight matrix. And so what's your take on that? What's your viewpoint on that?
Still, even on the GPU, the biggest problem is we just don't have enough memory bandwidth. So we in my project reports, sorry, let me pull a graph up. We really don't see too much acceleration on GPU and CPU. Typically, you get at worst 10 times the the speed on a GPU versus a CPU. But in the case of HTM, we only get something around 2 to 3 times. So we have to sort out the memory bandwidth issue before we can have fast HTM. But that won't be the case if we are still using GPUs and CPUs. But again, building custom chips is way too expensive, even in academia.
Okay, anything else for Martin?
So for this graph that we're looking at for e-tailor performance, is this saying like how many learning cycles it's doing a second is close to 9,000? Is that what this is?
No, this is the temporal memory have 9,000 input bits and 9,000 output bits. And
okay.
Let me have a
look. So this performance is measuring the memory bandwidth.
No, this one is measuring how long it takes for one learning to run, one learning and inference cycle to run.
Okay.
I believe I'm doing about 1,000 cycles in average in lab.
So here I'm sorry, if you were still talking, man.
Yeah, sorry. The very curious part is HTM.core has this very weird performance trend where it's slower at about 200 cycles, 2,000 bits, and you cross over some threshold and suddenly gets faster and then keep on going slower. I don't know why, but this is a very interesting observation.
Maybe the bits are aligning in memory, so it's flowing more easily without having to do any re-grab some memory from the CPU to the RAM.
Yeah, yeah, but yeah.
So Martin, there's a question from Falco. He's watching on Twitch. How is your dissertation received?
Sorry.
How did it go when you presented this for your dissertation?
Oh yeah, I gladly how do I say? I turned out to be the first. Oh gosh, I don't know how to say this in English. Sorry. I believe Max, you speak Chinese?
好像我在大学是学中文的专业，不过我的词汇还是比较小。
I'm sorry, because 我比赛拿到第1名。
比赛拿到第几名？
Yeah.
第1名吗？
Yes.
Oh, so he was in first. He's a winner.
That's great. Congratulations.
Yeah.
You should remember that English word.
Yes.
第1名就是可以说是 winner 吧。
Yeah. I don't know how to accurately translate it.
Yeah, you were first place. 排行第一。
That's very good. That's the best.
Yeah.
Thank you. Marcus, what was your question again?
Sure. So in this, I'm looking at the line and I'm trying to see if one of the classic things that that HTM runs into that can slow it down over time is that it's always adding dendrite segments to the temporal memory. So depending on what data set you're passing into it, some of them, like if you just pass in random noise, the thing just slows down to a standstill because it doesn't have any signal to latch onto. And by default, it doesn't have any code that cleans it up unless you go and add something like that in. And I'm just wondering, so in your code, you have a full, your temporal memory must have multiple segments, multiple dendrite segments. You're doing all of that, but you're still, are you running into that issue at all, or were you able to avoid that issue?
So Ettler runs on one segment, and in this graph, HTM.core also runs on one segment.
Okay, that's
and
good.
The approach Ettler takes is we only have one segment, but we have a lot of synapses on that segment.
Okay.
And in this graph, I'm sending random noise into it. So this is the worst case scenario.
Okay.
And what Ettler does when it has a full list of synapses is you can prune those synapses periodically. And this is what's happening in the graph. So I believe I'm not sure right now. I clean the synapses every something like 150 cycles. I'm not sure, but yeah, it cleans the synapses, and you end up with usable space, and you can grow again.
Let's see. Thank you.
That's really impressive, Martin. Congrats on coming in first with your dissertation. And unless anyone else has any comments or questions, I don't think Jordan K is here, unless you are. Let me know if you are. And otherwise, if anyone else has something they would like to present to the community, please raise your hand in Twitch. Sorry, not Twitch, Zoom. And go ahead.
Can I say something about the project I'm working on?
Yes, please. Please let us know who you are.
I'm Hyun-Sung Go from the forum. Yeah, I'm actually working on a project that implements the entire HTM on NumPy. Let me just.
Sure, you're gonna share your screen. Oh, perfect.
Oh yeah. Yeah, the GitHub repo is here, and I actually finished implementing the HTM part. Yeah, it runs entirely on Python, but the interesting thing is rather the NumPy is a very similar API to PyTorch, so everything here just can be dropped into PyTorch to run on GPU. So that's basically what I did here. I implemented basically every aspect of HTM. The performance-wise, it's not that great. Probably worse than Ettler. It runs dozens of milliseconds per step.
Well, is that with like how many columns, and what's the size of the input?
Yes, the 48 cells, columns, and 32 cells per column. A big difference between Ettler is that it actually implements multiple digital segments. So yeah, a cell can grow segments to, yeah, I guess that's the project I'm working on. I'm testing it with, text prediction, natural language stuff. I'll be posting it when I'm done. Yeah.
So how are you encoding the text? Yeah.
Oh yeah, I'm actually encoding the text by, some sort of auto encoder. It's just pure deep learning stuff. I haven't really successfully implemented the decoder yet, but I think I'll probably use deep learning stuff, I guess.
Sorry, Hisong, I cannot hear you.
Oh, sorry.
Your voice was a bit mushy when it comes to my end. May you
It was
say again?
same here. Could you just repeat how did you encode? You said an auto encoder.
Not exactly auto encoder, but rather it's forward to back.
Sorry, it becomes mushy again.
Oh, I'm sorry.
Every time you say something important, it breaks up.
Oh,
The Skynet is stopping us from building something.
yeah, it's just a simple linear word to back network, and it really has a loss function to some sort of sparsity.
So this is similar to the Numenta's PyTorch implementation, right? Because you were working on this. You had part of this complete before we released the sparsity, the paper, the why are we so dense paper.
Do you mean the deep HTM I posted like a year ago?
Yeah, I think so. Because we were just talking about. I thought it was you who on the forum. We were having conversations about how to sparsify neural networks, and we were talking about it.
Keep in mind, this is NumPy. This is basically changing over from something coded that uses our sparse matrix to something that is coding from scratch using kind of pure Python and NumPy. This isn't making the leap to PyTorch or TensorFlow. It's not that.
Okay.
No. Oh, it's implemented on NumPy initially, but it's currently ported to PyTorch.
Sorry.
And and it works.
Hyung-sung, it's very hard to hear you. I'm sorry.
Sorry.
But we're looking forward to you showing this sometime on the forum, right?
Yeah. I'll be posting it sometime soon.
Yeah, good call. I overlooked that you were talking about Torch, not NumPy anymore. So that's cool.
I'm sorry. It's just my first time talking in English.
Well, you're doing a good job.
Thank you. So basically, I implemented the entire HTM on NumPy and ported it over to PyTorch, and it runs about dozens of milliseconds per step, and yeah.
Sorry. I'm gonna ask.
I feel we did get the gist of it. Most of this did come through. There were a couple sentences there at the end that we lost due to bandwidth, but we saw it.
And I'm totally familiar with this line of work because I was so surprised to see basically Hyung-sung was posting results of this network even before we had released our code behind that paper, which I thought was really impressive, just based on the ideas.
The thing I posted on forum is something different. That's differentiable HTM, and this is just binary.
Oh, okay, I see. Yeah. Okay. Any questions or comments for Hyung Sung Go? Thank you for sharing, and for first time talking in English, it was very good.
Thank you.
Okay, I'm going to, we're back to our, so does anyone else, okay, Sam Heisman, that's good to see you. Why don't you join in?
Hey guys, first of all, awesome, amazing work by you guys. So impressive. It's like really awesome to have this meeting. It was a great idea. I didn't have a plan to necessarily share this, but I was kind of, it's like, all right, I've been working on this for like the longest time, and just like super quick. So I thought, let's see, where is it open here? Okay, so maybe I'll just share my screen really fast. So this is a, let's see, okay.
Let me just say while you're bringing that up that Sam Heisman on the forum, he probably knows the most about NuPic and building things with NuPic than any non-Numenta people.
Wow, really? Thanks.
Well, you've built a lot of stuff with, or you've tried a lot of things with NuPic, and you're answering questions very well in the forum, and I do appreciate that.
Thanks. Yeah, I figure like there's a lot of stuff I don't know the answer to, so if there's something I do, I can like jump in maybe. But okay, so my screen is not sharing, I'm assuming here. Okay, open system preferences. I'm going to try this for 1 second. If it doesn't work, I'll just make a post, or I could just summarize it really fast. I wanted to show it, but okay, so basically this is just a paper that I've been working on for a long time that I finally submitted that applies HTM using NuPic to biometric identification. So trying to recognize if someone is sort of that person, but instead of based on like their fingerprint or based on looking at a picture of them, it's based on their sequences that they generate while playing a game, while doing a task. So applied HTM to that and basically got some what I think are hopefully pretty good results to show that if you have a bunch of, basically the upshot of it is if you have a bunch of people do like a simple task, like a generic task enough times, they could start to generate like sort of like idiosyncratic patterns that you could use to, especially if they're consistent, to identify that it's that. If you don't know like who's playing and you see somebody playing, you'd be like, oh, this looks like Matt, because Matt has a certain way of generating sequences within the context of this game, so where we could separate them out from other people that are trying to do that. And there are certain people that it seems to do a really good job at, even with like a really small amount of data. I actually reduced the data size by doing like time chunking, like time aggregation. So maybe fewer data points that have more time to them. That actually like helped the system a lot, even with only like a couple hundred data points to train on. Like it was like finding the right person out of like 40 people based on that like small amount of information. I'll make a discussion post. I don't want to like bore everybody, but I thought it would be better if I could show the pictures, but in any case, finally submitted that. Don't know if it's going to get accepted yet, but yeah, just like using NuPic and stuff. So
wait, what did you submit it to?
IEEE Human Machine Systems.
Oh, so it's a competition, or is this a paper you wrote about this?
It's just a paper. It's a journal submission.
Oh, cool.
So
do you remember in like 2015 there was a hackathon submission where someone would identify people based on not the password they typed in to the keyboard, but the timing of the up and down keystroke events?
Yeah, that's right.
That reminds me of that.
It's like that. Yeah, I think it was there was Numenta Rogue. There was a project. I remember Scott told me about it at one point, to like notice like if somebody got up from the computer and somebody else sat down and started typing and you wouldn't know. So yeah, so it's along those lines. But yeah, so anyways, I've been like really supported by Matt and a lot of people for a while, so definitely like wanted to share that if it comes through. If it like gets accepted, I'll maybe make a post about it. Yeah, so just wanted to say that. And next we're going to do workload assessment. So like somebody's doing a task and you want to figure out in real time like how much effort are they having to put in, how difficult is this for them. So the idea is like if they're being more consistent and predictable, then they're having an easier time. If they're being more chaotic and unpredictable and having all these high anomaly scores, maybe they're like having a harder time. So like that's like the next part. Anyways, thanks guys. You guys are all awesome.
That sounds cool, Sam. Mark, your calendar needs to be flipped.
Yes, it does. Question for you: the anomaly detection, would that work on handwriting identification for who's signing?
I believe so. Actually, there's some benchmark data set that I got. I haven't actually used it yet, but there's benchmarks for this. I actually had that exact idea, and I don't see why not, because you could just encode it in some kind of a basic like XY coordinate space or like 2 dimensions. But I've actually used that example to describe this idea to people, because I think that would really like show it well. Yeah, because like if I were to like forge your signature, if I had like an hour to do it, I could probably like do an okay job. But like if I had to do it in the same amount of time that you actually signed in, then for like very small chance I could probably actually do it well. So yeah, that's like a really good idea, I think. Thanks.
So I'm acting as Falco's proxy because he's watching on Twitch. He's asking if you have to calibrate the idiosyncrasies of the different people, or does it just automatically learn to identify them?
So yeah, so it automatically, because what you do is, so let's say you have like 40 people that play, and you have a training set or a learning set basically for all 40 of those people, and then you generate 40 different models, 40 different new pick instances, right? Yeah, and then you have a test set for all those 40 people, and then you have a test set, like let's say somebody's playing, you don't know who it is, turns out to be Matt, but you don't know, it could be any of these 40 people. You bounce that test set off of all of those 40 trained models and look at the anomaly scores that come back. And if there's a model that was trained on Matt's other playing, then the idea is those anomaly scores will be lower from that model, because that model is used to seeing Matt play, as opposed to the model that's used to seeing me play or Mark or whoever else, So yeah, that's the concept there. So it should be generalized to different different tasks also. Different people are different tasks, as long as obviously, right, there's like periodicity in the sequences, like with HTM needs. So thanks. Yeah, good question.
Sounds cool, Sam.
Yeah, thanks, guys.
Okay, so I'm open it up to anyone else who wants to comment at this point.
Hey, Matt, may I share a bit of results from doing neural networks and HTM together?
Yeah, please do. You can share your screen.
Okay, thanks. So this is a bit of research that I think it's going nowhere, so I'll probably just share it and hopefully someone could take it further and even make it a paper. So what I've been doing is, when Numenta released the sparsity paper and sparsity and convolution neural network paper, I did a bit of experimenting with sparsity and adversarial attacks. So what I ended up finding is, well, on MNIST and like K-winner algorithm is pretty strong against quite a wide range of attacks like IFGSM with even 1,000 iterations. It really can't break the neural network protected by the K-winner algorithm, and the others are just got blown away. And even this even works pretty well against other attacks like deep full and single pixel attack and EAD attack on the MNIST data sets using LeNet5. But not shown here, but when it moves on to larger data set like CFAR10 or ImageNet, K-winner simply just doesn't work. I don't know why. So if someone could make it work on CFAR10, even ImageNet is definitely paper worthy, and even possible to go on to CVPR, but I don't know how to get it work. And yeah, just sharing, and hopefully someone could pick it up and keep on doing the work. Thanks.
Which data sets though?
I'm running on. You mean the successful one or the failure one?
The successful one, the first one you showed.
Oh, MNIST.
MNIST, okay. Thanks.
Yeah. It probably will also work on the MNIST for ladders, but not CFAR10.
So I don't think we've done any testing on specifically adversarial attacks, but it makes me feel good that that those numbers came out, because I would expect it to do better against adversarial attacks, like you would do against MNIST.
Yeah.
Martin, do you have any intuition why it works on MNIST and not on Cypher?
My guess, and this is pure guess and what I gather from experiments, is that one theory on how adversarial attacks is it nudges your neurons to very very high values, or it nudges your neuron in a weird pattern such that your later layers just doesn't accurately predict stuff. So what K-winner does is it prevents the very bottom end of the neuron from firing, so they are not affected. And one thing you can do to improve K-winner is, instead of just choosing top K, you select the top M to the top K plus M neurons. So you ignore the top M neurons. This will slightly improve the protective performance. So it also, by also preventing the neurons with the largest values to fire, to go on very high values to affect the lower neurons in the lower layers.
All right, thanks.
Why? Yeah, so the middle neurons must have enough predictive capability to tell you what is what, but the top neurons won't affect your prediction. You mean these? Yeah, all the time. This is my hobby. All the time, to get the best performance.
Thanks. Sorry, Falco. Okay. Anybody else?
I do have one more question for Martin. So
this is Lucas Souza, by the way.
Why did you decide not to pursue this? You said
because
it's probably not leading.
Sorry, what? I cannot hear you.
You mentioned this is probably not leading anywhere, but you showed actually very good results on MNIST. So
yeah, because I have been banging my head to this problem for 3 months, and I just can't get it working on cPart.
I see.
And each run took me like 2 hours on a large server, so yeah.
Do you have the code?
Yeah, I have the code. It's on GitHub, somewhere in a forum post. I can DM you later.
All right. Thanks.
All right. Thanks, Martin. So it doesn't look like anybody else. Oh, Axel.
Yeah, thank you. Can you hear me?
Yes.
I'm trying to be as quiet as possible. It's 4 a.m. here, and my wife will beat me if she hears it. Okay, I just wanted to quickly bring up the topic we discussed like 2 hours ago about parallel and distributed workload. Here's the issue I thought about for a very long time, and I don't have a solid solution for that yet in mind. I wanted to quickly discuss it. If you employ the standard approach, classic approach, and straightforward approach, this problem is not appearing because you just wait. You just wait for the results to appear. For every cycle, there is a cycle. But if you distribute that workload, there is no cycle anymore. There's just a constant flow of interactions between enormous amount of actors, and they can be on a different nodes. And here's the problem. If they are on local machine, they operate with one type of latency, local latency. Well, I don't know, CPU, memory, and stuff. If you distribute it to the other nodes, there's another type of latency, network latency, and it's another timings, different timings, and somehow we need to synchronize that stuff to be able to produce, I don't know, more or less reliable results. How would we fix it?
I have a thought on that. So basically, we wouldn't need to get all the results back. For example, we wouldn't need every single column out there in the network to come back in order to reach some sort of conclusion. We could take a partial subset of the responses that have come back to, say, like the pool manager, for example, and just run with that. One addition to make sure that time steps aren't conflicting with each other is, say, each time step would get its own hash, so that when you distribute this broadcast message out that starts the cycle back and forth between the pool manager and the columns, that hash would ensure that while the rest of the pool is moved on, that incoming responses from perhaps very latent columns wouldn't mess with anything. Perhaps even have some sort of, so in the Elixir Gen server universe, maybe have the pool manager have a specific call, a specific call function that says, here's our current hash that we're on, our current time step that we're on. So, at a random interval in each column, have it check in with the pool and say, hey, where are we at? And then, if it's too far behind, it'll drop away. But I tend to think biologically in our brain, it's not like there's no central operator like the pool manager that's waiting patiently for everything to come back. Things are just kind of going when they go. Like the neurons are firing when they reach their potential, and they do it. So maybe I'm mistaken, but my understanding is that even in our brain, there's latency between different parts, and that it doesn't really seem to matter other than those instances where perhaps we have deja vu or sort of other artifacts of even biological latency within our brain as different distances are firing within. So at least that's my thought. And
I think Mark Brown has something to say about that.
You bet I do. There is synchronization in the brain. The brain waves, or theta, alpha, do synchronize entire areas, and they sweep through. Everything is based on that as a clock. So if you look at some of the data that they've been gathering from imaging studies, there's definitely synchronization within an area and between areas. HTM assumes that there is a cycle. It starts out, runs for everything getting updated, and then it does it again. That roughly corresponds to the same thing as one alpha wave of brain activity.
So if we were to build in some sort of timing or maybe a timeout mechanism, then
I'm not so sure if timeout is perhaps an idea of a token or a semaphore.
Yeah, well, I mean, so say we have a token, semaphore, whatever scheme. At what point does that no longer become the valid alpha wave, if for example?
Well, that's the whole point. Is it runs for 1/10 of a second, or alpha is roughly 10 hertz, so it's roughly every 1/10 of a second. Whatever is done, and that's this cycle. That's the current state of the entire area that can be passed on to another area. Then that's passed on with, depending on which layer you're at, 2, 3 projects with the long axons, 5, 6 bounces through the thalamus, and so forth and so on. But each particular time step is basically one alpha cycle.
Like,
I'm not sure how you do that with your asynchronous agents. That they're not really based on the same concept.
I mean,
it seems a bit tricky to work in these oscillations and waves into the Elixir actor paradigm, perhaps.
Maybe we could send some kind of synchronization message. I don't know.
Yeah, I don't feel like it's definitely tricky, but maybe I'm being too naive to think that it shouldn't be a barrier. So.
I have an oldish post that's been on the forum for, I don't know, 2-3 years now that basically discusses that, and it has some discussions on the cycles and some of the mechanisms that are in the brain. I'm not sure if it's an easy thing to find, but it's been around a long time.
Well, Mark, could I entice you to learn Elixir and get involved at poking it?
I'm working on some other projects myself right now that are taking all the time I have.
All right.
Max, I just want to comment on the subject. One thing that neuromorphic processors do is that they don't guarantee that the message will arrive at exactly the same time step, but they guarantee that the message will arrive in a set of melt-up time, let's say 10 milliseconds or 10 microseconds. And then they simply say, well, each of my timestamp must be larger than 10 microseconds. And it will synchronize automatically. This is what chips and the neuromorphic computers are doing.
Yeah. And
one of the
we could distribute our counter, by the way. So like right now there's just the single pool manager that's receiving all the completion messages from the columns essentially. And we could even distribute that out so that it isn't dependent on a single process being tied up in a single scheduler as well. So we could reduce latency, or at least distribute the latency.
Well, in your own brain, what happens is if things happen within a certain one alpha wave bucket, they're simultaneous. There's an example in that post I have a linked video where they're talking about if you're watching somebody bounce a ball and they're walking away from you in a large arena. As you watch them, you see the ball synchronize. It all looks good. It's the same time step because it falls within the same alpha cycle. When they get a certain distance away, the delayed sound suddenly breaks that illusion and everything looks very strange at that point. So there's definitely buckets of perception. If everything falls in the same bucket, it's the same event.
Cool. I'd love to have you guys, get involved with the Elixir stuff because it's pretty approachable and it won't bite you if it messes up. So, yeah.
Okay. Anybody else? We're having a good long meeting today.
Okay. The BAMI thing, you want to put that out and see what interest there is?
What's that? Just tell people about BAMI?
Wikifying it.
Oh, yeah.
Community input. Okay.
Well, yeah. So Mark had an idea. We haven't put a lot of effort into BAMI, the Biological and Machine Intelligence document, for a while. I haven't run this by any of my peers at Mint at this point. But he had an idea, why don't we just put it out in the public domain, Wikify it, and let the community sort of take over, write the temporal memory section, which we haven't finished. And I thought, I'll throw that ball and see what happens. I mean, honestly, anybody could do that at any time. We wouldn't stop anyone in the community from taking that content and building it out into a wiki. As far as me sort of getting that ball rolling on my end, I'll see what the rest of the team has to say about it. I think it's not a bad idea because I don't see us putting a ton of energy into that document right now. Is it anybody out? I mean, if we did that, would anyone be interested in helping sort of take that document to the next level, filling out the things that are not right? There's some things that are a little bit wrong. I don't know if there's anything blatantly wrong, but there's things that should certainly be updated in it. And then there's complete chapters that are missing.
I already have too much to volunteer time, but I sure would like to take a crack at it.
Do you have a link for where that material is currently?
Yeah, I'll post in chat in a minute here.
I will add that as far as it goes, everybody here has probably started out with on intelligence, but I personally got an awful lot going through BAMI and actually working through the pseudocode and getting an idea of what's actually happening. For me personally, it was extremely helpful. And I know some people came in via the videos, but the BAMI thing, I could sit down and kind of slowly work through it at my own pace, and that was very helpful to me. So if that was updated to where it was actually current and people felt better about it in terms of being up with the current model of how HTM works, I think it would be very helpful.
Yeah, I agree. If anyone hasn't looked at that document and you want to understand HTM, it would be if I could only give one reference to someone, I would probably give that. Okay. Happy Hackers Hangout, everybody. Thanks a lot for joining. I wanted to have a big one, and we had a big one. We had like 16 people on Zoom. There was maybe 10 people on Twitch at some point. So I really appreciate everybody showing up and sharing your projects. I think the community is going to take a lot of this stuff and run with it, and that's sort of what's happening right now. And I love all the work that you guys are doing, and I think you guys are on the right track with this distributed processing thing. That is it's a big problem that needs to be worked out, and I think it could lead to a lot of advances, especially as hardware matures. We'll be ready for it when it comes. So appreciate everybody, and take care. I'm gonna go ahead and end the meeting, and I'll see you guys on the forum. I don't think there'll be a research meeting tomorrow, but next week for sure. All right, take care. Thanks for joining, Marcus. And thanks everybody on Twitch for joining and watching. I don't know why I'm trying to press buttons that aren't there. Okay, stopping the recording. Bye guys, bye everybody.